ISFE webinar entitled A Novel Membrane Combination Process for the Non-Thermal Concentration of Juices and Beverages by Dr. Carmen Moraru from Cornell University. Dr. Carmen Moraru is a professor and chair in the Department of Food Science at Cornell University. She received her bachelor's and PhD degrees in food engineering from the University of Galati in Romania. After working briefly in the dairy industry, she became a faculty member at the University of Galati. In 1999, she joined the Department of Food Science at Rutgers University as a postdoctoral associate and then as assistant research professor. She joined the Cornell faculty in 2003. Her research focuses on using novel technologies for improving the quality and safety of foods, with a focus on membrane technologies, light-based treatments, and high-pressure processing. She is an active member of the non-thermal division of the IFT and served as its chair. Finally, she received an Outstanding Service Award from this association in 2017, the International Dairy Foods Association Teaching Award in Dairy Manufacturing in 2015, and in Dairy Foods Research in 2013. Please, everybody, before we start, remember to mute your microphone during the presentation. If you have any questions through it, you can write them on the chat so that you do not forget them. And at the end, if you prefer, you can ask them directly to the speaker, or I can also read them aloud for you. Please welcome Dr. Moraru. Thank you for your time for this presentation.
Thank you, Viri, and good morning, everyone. I hope you can hear me well. It is a pleasure and an honor to speak with you this morning, and thank you for logging in. I looked at the names. It appears that many of you are actually from Latin America, and that is wonderful, but wherever people are, warm welcome to everyone. When I was asked to give this webinar, I was contemplating a number of topics, and then I thought of something that is rather new, a technology that we developed in our lab, and we are working on it at the moment, and I think it is very relevant, and I hope that you will find this talk interesting. How I decided to structure this presentation, and if my, okay, my mouse is working now. I'll give you a brief introduction. We'll go over the basics of membrane filtration just a little bit to make sure that we all have the same jargon. Then I will go into more details about the two processes that are the topic of our discussion today, namely reverse osmosis and forward osmosis. And then I will present to you a few case studies on the use of these processes, either separately or in combination for concentration of juices and beverages. In terms of introduction, why do I think this is a very important topic? Because if we look at food consumption and if we look at trends in terms of various foods that are manufactured, we notice that juices have actually developed quite a bit in the last few years. One of the reasons is also the developments in non-thermal processing, and now we can have juices that are made from various fruits and vegetables that are very colorful, very nutritious, and we like these juices a lot in the US and all over the world. In the US alone, and this is just some old statistics that I have here, relatively old, 2015, we drank nearly 7 billion liters of 100% juice, and we're not at the top of the consumption chart either. But as we all know, juice production is seasonal. And if we want to have juices stored over the year so that we can consume them off season, it is often practiced by the food industry to concentrate them because if we were to store the single strength juices, they occupy a lot of space because of the high water content. And then, you know, it takes a lot of resources to both store and transport, plus the juices can be prone to degradation either by microbiological or chemical mechanisms. So a solution that is often used by industry is concentration. And if you look at this chart here, there is a trend in terms of the market for juice concentrates in the world that is going to increase. It's predicted to increase even more as we look forward from 2019 on. We're right here now. And that is really as a direct result of the high demand of juices throughout the year and wherever we might be in the world. Now, how are juices typically concentrated? By thermal evaporation under partial vacuum. And the beauty of thermal evaporators is that they can accommodate very high capacities and they can reach a high concentration level. 50, 60 Brix is something that the juice industry often does. There are some drawbacks to thermal concentration, and we are quite familiar with the loss, partial or total loss sometimes of thermally labile components that otherwise have bioactive role, like vitamins. Vitamin C is a good example of that, or compounds like anthocyanins. They also get partially lost during the process. There are also undesirable changes in taste, flavor, or color of juices. Then, depending on what juice we are talking about, or expanding this to beverages in general, we may have Maillard browning. Also on the equipment side, in those thermal evaporators, we see fouling and burning on the heat exchange surface. And last but not least at all, this is actually a very significant element these days, is that thermal evaporation consumes a lot of energy, and as the industry is looking towards more sustainable methods of processing, this particular aspect is increasingly important. But if we look as consumers to the offerings on the market, oftentimes when we hear about juice concentrates, we don't hear about them with a positive connotation. As a matter of fact, the juice industry is often using this as an ad, not from concentrate, because concentrates are known not to have the greatest taste or flavor. So in recent years, there has been an increased interest in finding alternative ways to concentrate juices, and that alternative is offered, or one of the significant alternatives is represented by membrane processing. With reverse osmosis being currently used in some industries for concentration, both in the juice industry as well as in the dairy industry. I want to remind you that while I will talk a lot about juices, everything that I will talk about today applies to a great extent to other beverages, and dairy beverages are a significant component of that. And then there is another process for osmosis related to reverse osmosis that is gaining commercial interest. And we are going to look at these two processes in a lot more detail in the next few minutes. But before we go there, I just thought I would remind the audience, in case you're not, or just really educate the audience on some basics on membrane filtration, in case you're not very familiar with these processes. In membrane filtration, typically we have what we call a membrane, which is a semi-permeable medium. It can be made out of polymers, or it can be ceramic. And this has some very small pores that only allow selected components that have a size or molecular weight smaller than the pore size to pass through into what we call the permeate or filtrate. All the particles or solutes that have a larger size than the pores will be concentrated, and the stream that is resulting is called either concentrate or a retentate. In industry these days, we see most cases configuration of membrane processes as crossflow, which is what you have here. So the feed comes at a speed tangential to the membrane, and this is called either tangential flow or crossflow filtration. What makes these small molecules pass through the membrane? There is a driving force that actually allows that to happen. And that driving force, depending on the process, could be pressure difference. That is the most common. And this is where, reverse osmosis fits as a process. We have also other processes like nanofiltration, ultrafiltration, microfiltration that fit under this category of pressure-driven processes, where you have a pressure difference between the feed side and the permeate side that pushes the small molecules or particles through the membrane. We will talk today also about the process where concentration difference is the driving force of this mass transport through the membrane. There are other processes where we may have a difference in electrical potential. We will not talk about those though. So the nice thing about membrane separation is that it's a purely physical process. Sometimes it's described as a molecular sieving process. And there are no chemical modifications to the components that pass through because, again, the process is just simply physical. Then if things are so great, why isn't membrane filtration used more often than it is these days? Well, because it has its own challenges. And I will just point to the main challenge in membrane separation that you probably have heard about if you're familiar with membrane filtration. And those are related to concentration, polarization, and membrane fouling. What happens during the membrane filtration process is that you have an agglomeration of either solutes or small particles onto the surface of the membrane in this boundary layer. And this can cause this concentration polarization that will actually slow down the mass transport through the membrane. You may have physical pore blockage and even internal pore fouling. These last two are more typical of membranes that have larger pores. For instance, ultrafiltration, microfiltration are more prone to pore blockage and pore fouling, whereas processes like reverse osmosis are more prone to concentration polarization. Why do we care about these phenomena? Because they have very direct impact on how the process is going on. We will see immediately a decline in the permeate flux, which is the flow of permeate through the membrane. And this is very drastic depending on the feed that you have. The flux can actually drop a couple of orders of magnitude in value just in a matter of minutes or tens of minutes. And it also changes the retention characteristics of the membrane. This is, again, something that is more relevant for the larger pore membranes where you are effectively reducing the pore size by the pore blockage, because now you have blocked partially the pores and you're creating much smaller openings into the membrane, so particles that wouldn't otherwise be rejected by the membranes will be. For reverse osmosis, which will be the focus today, it's mostly concentration polarization. This reduction in flux will cause, of course, issues with productivity of your lines, and also issues with sizing the equipment and the throughput in the end, and quality changes as well. Which is why we have to acknowledge these processes that are not completely avoidable, and find out which are the conditions that would minimize fouling. So there are certain parameters that can be changed that would allow us to minimize fouling and thus allow fluxes to be retained for a long period of time. The membrane material and the structure of the pores and other physical characteristics of the membrane will have a significant impact. As a user of the technology, you rely a lot on the membrane manufacturers to address the issues related to the membranes, and there are quite interesting advances in membrane technology itself, in the fabrication of membranes that allows membranes to perform better. Our focus will not be on that today. We will talk more about the processing side. The feed itself is important, and very importantly, the interaction between the feed component and the membrane are very, very important in terms of how the process will progress. Obviously, if you have a feed that has complex concentration, complex composition, and will have high concentration, the process will be more prone to concentration polarization and fouling. And then the processing parameters are also very important, and these are the parameters that you can actually change during the process and would allow you to maximize the flux and reduce fouling. For pressure-driven membrane processes, transmembrane pressure is the driving force, as I mentioned, and up to a certain level, increasing the transmembrane pressure will maximize the rate of flow through the membrane, in other words, the flux. But at some point, when you push high amount of solutes or particles towards that membrane, actually increasing further the transmembrane pressure will lead to severe fouling and will effectively block your membrane, and then the flux will be reduced to zero. So there is an optimum level there of transmembrane pressure where you can maximize the flux, but beyond that, you are fouling the membrane even more. Crossflow velocity is generally considered to be a positive parameter for membrane processing because you are creating turbulence on top of the membrane, and that will dislodge some of the particles that may be stuck on the membrane otherwise. So you enhance the mass transfer through the membrane. In many cases, however, crossflow velocity and pressure will go hand in hand because you're using high pressure pumps to push the liquid into the membrane system. So there is a limitation to increasing the velocity, the crossflow velocity as well. Temperature has a positive effect. Increasing the temperature typically decreases the viscosity, which is beneficial. It increases molecular mobility. But if one of the reasons why we want to use membrane filtration is to work at low temperatures, then we have to be mindful of that and not use temperatures that can cause chemical changes. So in many cases, processes are conducted warm at temperatures 50 to 50 degrees centigrade. But that could also lead to some microbiological issues, and that's why there is a recent interest in cold separation. With that introduction into membrane filtration, let's talk specifically about the two processes that are the main focus of today's webinar, and those are reverse osmosis and forward osmosis. For reverse osmosis, which is a pressure-driven process, we typically use that process to concentrate liquids by removing water or purify water, the process of desalination. And as a matter of fact, reverse osmosis is the oldest commercially used membrane filtration process and has been used for desalination for a century almost at this moment in time. So the membranes are really tight and only allow water or very, very small solutes to pass through. But ideally, we would only want water to pass through these membranes. In reverse osmosis, we need to use quite high pressures. How high? Tens of bars, hundreds of PSI for those who might be in the United States and use PSI as a pressure unit. Why do we need to use such high pressures? Because if we want to, let's say, concentrate a solution, a feed, by pushing the water through a reverse osmosis membrane, we have to apply a pressure that exceeds the osmotic pressure of the liquid itself. And the more concentrated the liquid is, the higher concentration of salts and sugars, for instance, it has, the higher this osmotic pressure will be. And that's why we need to apply these very, very high pressures to push the water out of the liquid stream, liquid feed through this membrane and concentrate it. And that is what the juice industry is doing, or the dairy industry is doing at the moment. They're using these very high pressures. What is the drawback of using high pressures? As I just told you a few moments ago, you will cause very significant concentration, polarization, and fouling. That's one of the drawbacks. But in any case, I want you to remember here that the water in reverse osmosis flows from the higher concentration into the dilute permeate side. Normally in juice concentration or milk concentration, for instance, you would have just water that is being pushed through the membrane. Let's take a look at forward osmosis, or actually, it's the normal osmosis process. What happens when you have two liquids, one of higher concentration, the other one of lower concentration, separated by a semi-permeable membrane, these two liquids will have different osmotic pressures. Thermodynamically, there is a tendency for the equilibration of the concentration between the two. So basically, the solute, let's say, the solvent, I'm sorry, let's say water in most cases of interest for food applications will actually tend to dilute the concentrated side so that the osmotic pressure between the two sides is equal. Now, if you had concentrated liquid on this side, a very concentrated liquid on one side, and the dilute one here, you can effectively move water through the membrane so that you concentrate the diluted side. And this is how forward osmosis is used commercially. You just use a different liquid on the concentrated side, which is called a draw solution, or sometimes an osmotic agent. And then you have the feed on one side and the osmotic agent on the other side, or draw solution. And the water is passing from your feed into the draw solution, diluting the draw solution and concentrating the feed of interest. Could be juice, milk, coffee, tea, your choice here. The driving force is the difference in concentration, which translates into a difference in osmotic pressure between the two sides. So when you operate forward osmosis, you actually have another element that is not common in pressure-driven processes. You have the feed side, and this would be your membrane here. So the feed comes in, dilute, water passes through into this draw solution or osmotic agent, and the feed is concentrated and moves on, and you actually recirculate that. In most cases, you recirculate, you don't get your concentration in one pass. But there is this other side that is now new to most membrane filtration users, that is the draw solution side. Because what happens now, you feed a concentrated draw solution into your membrane system. So this would be on the opposite side of the membrane here, where the permeate side would be in traditional membrane filtration. And then you would actually dilute this draw solution, which now becomes a spent draw solution, which you would need to regenerate. And this is an important piece because this is one of the limitations of forward osmosis, that you have to worry now about regenerating this draw solution. But this is something that can be done in different ways. It is more flexible than, for instance, concentrating a beverage or food, because there are less limitations in terms of the technologies that you can use for that. But be aware that this is something that you need to constantly regenerate, or if you have a source, a limitless source of draw solution, which never really happens, then you don't have to regenerate. But usually you have to regenerate this draw solution so that you can continue your process. So this is how forward osmosis works. There are some differences in terms of membranes between reverse osmosis and forward osmosis. For reverse osmosis, you have these very dense membranes. In both cases, you have a very dense separating layer, and then you have a support layer. On the reverse osmosis side, here you actually see these membranes that are schematically represented to be sturdier because they have to withstand those very high pressures. For forward osmosis, they don't need to withstand those very high pressures. And as a matter of fact, the support layer has to be rather open because you have to now have the draw solution reach into this layer and create that osmotic pressure difference. So you don't want it to be too dense, but that can cause some problems in terms of mechanical resistance. So I just wanted to show you, some structures here for reverse osmosis versus forward osmosis. See, they are quite similar to the schematic drawings that you saw, much more open for forward osmosis on the porous side. And this actually still needs to provide sufficient support for the active layer. Now, we talked about concentration polarization. Does it occur in forward osmosis as well? Yes, it does. It's just a little more complex in forward osmosis because now you have two fluids. So remember, water passes through, and then you have that osmotic agent on the other side of the membrane that typically have some has some solutes in it. Could it be sugars? It could be salts as well. So some small solutes that are here would have the tendency to actually pass through the membrane, and if they find an imperfection in the membrane, they would actually flow back into the feed, and we'll talk about that in a second. But that's not the purpose of this particular slide. What I'm trying to show here is that you would have concentration polarization both on the feed side, where it's similar to what happens in reverse osmosis. You have what we call a concentrative concentration polarization, or more precisely, external concentration polarization, because it occurs on the outside of the membrane. But there is also concentration polarization that occurs in the support layer, because now you have water that's permeating through here, and that means that it's diluting the osmotic agent at the interface. So if we look on the left-hand side, what would have been the osmotic pressure difference between the feed and the draw solution, now effectively it shrinks to much smaller effective osmotic pressure difference, because you have actually a higher concentration of solute here and a lower concentration on this other side because of the dilution of water. So you have to be mindful of this too. This is not irreversible, and moving these fluids at higher velocities will help diminish those concentration polarization effects, but you have to be mindful of them. I mentioned to you the possibility of the solute passing through the membrane. If there is any breach in the membrane, you may have the solutes in the draw solution passing through. We have experienced, a case of a breached membrane because we used this membrane for a long period of time, and we were experimenting with it. So we could actually see some passage in an experiment that we did with milk, some passage of the potassium lactate that was our draw solution into the feed at concentrations that were too small to actually detect easily using regular chemical analysis, but we did some NMR work, and we noticed peaks for potassium lactate into concentrated milk because of the this draw solution reverse flow. What is the main message here? That you have to have a food grade draw solution just in case this reverse flow occurs. It shouldn't, but if you have a sudden breach in the membrane, you don't want to have any adulteration of your product or any contamination with a substance that is not food grade. So that's just food for thought. I tend to always show possible drawbacks so that we are aware of those when we develop processes. Just a final comparison between reverse osmosis and forward osmosis. Again, for reverse osmosis, you need very high pressures, very large pumps, and limited achievable concentration because of the membrane fouling at very high concentration levels. For forward osmosis, the membranes are less prone to fouling. You have smaller flow rates through those membranes, smaller pressure differences. That's why you can achieve higher concentration levels, but you need a draw solution, and the process at the moment is less developed for food application. The other thing, just briefly, the fluxes in reverse osmosis at low concentrations at least tend to be a little bit larger than in forward osmosis, because you have this driving force that will be typically larger. And I'll show you some data about this in a second, because this holds for a while, but then when you hit concentration polarization, then the situation is actually reversed. So here we are at the last portion of our webinar that really shows the applications, which I suppose is why you tuned in today. So let's take a look at some data. Some is pre-press. A small portion of it has been published, but we're very actively doing research in that area at the moment. For reverse osmosis, we use a homemade unit. We just use a commercial reverse osmosis membrane. I don't have the manufacturer handy. I wanted to show you the small forward osmosis unit that we use in our lab, and we are currently actually building a pilot scale forward osmosis unit. But I just showed that to you because there are such units that exist, and you can conduct experiments at a small lab scale. Ours comes from Ederna from France, but there are other manufacturers out there. And as a draw solution, we use potassium lactate of about 60% concentration, and the osmotic agent is regenerated using a vacuum evaporator. The membrane is cellulose triacetate. We're hoping to see more progress in membrane manufacturing because this is, in my opinion, a little bit of a drawback at the moment. We need somewhat sturdier membranes for forward osmosis. But let's look at some data. And I would like to acknowledge my colleague, Dr. Olga Padilla-Zakur, who has shared this data with me. We both work on the same unit. And this is one example of a fruit juice, tart cherry juice. This is a juice that's very, very sensitive to thermal evaporation. The taste will change significantly, and the anthocyanin content will drop quite a bit. Actually, if I can draw your attention to the right-hand side here, there's just the very first set of bars, which shows the anthocyanin content after thermal evaporation and after concentration using forward osmosis. You see, it's just simply hard to compare. Forward osmosis clearly preserves very well the anthocyanins because there is no heat damage. This process was conducted cold. And then this difference is maintained, and then you have a degradation that's caused by storage, but still the forward osmosis concentrated juice comes on top. So you can see how the process started with a little bit over 10 bricks and then reached about 60 bricks, which is where the industry wants to go. So in this proof of concept, this is wonderful, but if you look at the x-axis here, time, it's a very slow process. Obviously, in membrane processing, you can scale up by increasing the surface area of membrane that you're using so that you can produce larger volumes, but nonetheless, it is a rather slow process, but the quality of the product is impeccable in the end. Another example that we generated in our lab, some data for milk, where we concentrate both skim milk and whole milk with forward osmosis. This is straightforward osmosis. Skim milk, because it doesn't have the fat globules, does better. You can actually get higher rates of water removal compared to whole milk. And when we run the process at 15 degrees versus 4 degrees centigrade, you do get some beneficial effect of temperature. So the process is faster at slightly higher temperatures. But remember, we're doing this as a non-thermal alternative. We don't want to have too high temperatures, and that's why we prefer to actually take a trade-off here between processing temperature and speed of the process. One example that really sets the stage for the combination process that I promised I'll talk about is the concentration of a stream that is a byproduct from the dairy industry. And this was a perfect example of a product that has low concentration. It starts with a little over 5 bricks in terms of the initial concentration. It is challenging to concentrate using thermal evaporation because it has high acidity, high lactose content, so it's really not doing well in thermal concentration. And then we looked at concentration by either a reverse osmosis or forward osmosis. So let's take a look what happens to the concentration on the left-hand side using reverse osmosis. Yes, you can concentrate that. The change in Brix is shown by the blue lines and the concentration factor by the red lines and data points. So if you look here, you can concentrate this from about 6 Brix where we started to a final around 20. The rate of water removal was fast initially, and the concentration factor increased quite a bit, but then we hit the plateau. On the right-hand side, we see something a little bit different. We see a much slower process initially, but then in the higher concentration range, once we hit a concentration of 15 Brix or so, where we see more of a plateau in reverse osmosis. In forward osmosis, that's when things pick up. Why? Because you need to remove a lot of water initially. You need to dilute a lot of osmotic agent here. The process really does very, very well when you actually get to those very high concentrations. So our idea then was, how about we maximize the benefits of the two processes by combining them, which means that you start off by reverse osmosis. This is showing the flux on the left-hand side and the concentration on the right-hand side. So I will refer to both. So you start by removing water with reverse osmosis. You start at a relatively high flux, and I didn't mention earlier, the flux is quantified in liters per square meter an hour. That is the unit for flux in membrane processing. So you start around 30 liters per square meter an hour, and then you bring it in the single digits after some time. And then you switch over to forward osmosis where you have comparable fluxes at that point. But what is the nicest piece of data to look at is what happens with the concentration. Remember, I mentioned to you that reverse osmosis plateaus at some point because of severe concentration polarization, but this is where forward osmosis really picks up nicely. So now in a fraction of the time that you would have seen otherwise, you get to a concentration level that's really high, that is comparable to what thermal evaporation will do, but this is a completely cold process. This is happening, all of this data here, it's happening at temperatures below 8 degrees centigrade, so it was around 7. By the way, this data is published, and you will see there is a paper in Journal of Food Engineering that was published recently. So it shows proof of concept for combining these processes, and we really believe this holds a lot of promise, particularly for dilute streams. A lot of the fruit juices that you see out there start with low Brix, so you can start with this reverse osmosis concentration first, and then finish it off with forward osmosis. You can do forward osmosis all the way through, but based on our calculations, it is more economically efficient to do it this way in a combined manner. Now, of course, the question always comes down to economics, and we'll talk about that in a second. This is just an example of how far we were able to go with this very challenging stream. And this is the water that comes out of it, clean water. So you can actually utilize this water back into the process for cleaning purposes, for instance, so that you minimize your water footprint of the process. I borrowed this chart from Ederna, who is the manufacturer of forward osmosis. So it's based on their data, but they actually determined that the concentration using osmotic processes, they're engineered osmosis processes a little bit different than what we have presented here. They're using it a little bit differently, but anyhow, by this osmotic process, you can get a much lower energy consumption compared to evaporation. And to put things in perspective, spray drying is high up there, but we're not talking about drying today. We're talking about concentration only. So I would just refer to these two boxes down here in terms of the energy consumption. And this, of course, does not consider the quality, which is something that, you know, it's hard to put a direct price on right away. So in conclusion, I strongly believe that forward osmosis is on its way of becoming an attractive method for the non-thermal concentration of juices and beverages. And this is particularly useful when you have a liquid that starts with very low concentration and you need to concentrate to 50, 60 Brix, which you can't reach using reverse osmosis. But reverse osmosis can play a role. You can use that in a combination process. You can start it off with reverse osmosis. And then in terms of the economics, we have done some calculations in our paper that's published. I chose not to show it here because for commercial applications, the economics will look even better because we did these calculations on the economics of the process based on our small scale mismatched forward osmosis and reverse osmosis units. But when you work at larger scale, the energy consumption, the specific energy consumption per, let's say, liter of water removed will look much better. So if you're interested to learn more about this process, please don't hesitate to contact me. I wanted to acknowledge the people in my group who were responsible for generating the data, Pedro, Andrea, and Kyle. We had also undergrads who helped. We had a variety of funding sources to get us started in this area, and we have you know, some ongoing projects at the moment that are funded through federal funds. With that, I would like to thank you for your attention, and I would be happy to open this for questions. Thank you.
Thank you so much, Dr. Moraru, for sharing your knowledge with us in this occasion. And as you said, let's start with the question and answer portion of the webinar. If you want to ask the question directly, please turn on your microphone. If you don't want to and you prefer that that I ask the question, please write it down on the chat so I can read it. Okay. Questions? I can start with one. So if you're, well, I was going to start with the cost or the approximate cost of the process, but now that you explained it, if it is that feasible, what is stopping the industry to change to this kind of process? Like, for example, juices or milk in dairy industries.
Yeah, well, nothing really is stopping, but this is a process under development. So actually, there is a shortcoming at the moment that is represented by membranes, forward osmosis membranes that have not yet been developed to a point where the industry is satisfied with their quality. There are quite a few forward osmosis membranes actually that are used by the non-food industry. So there are some that are used for water purification, for brackish waters, for instance, residual waters. Even in a certain configuration, interestingly enough, forward osmosis can be used to generate energy because you use that flow of water through the membrane to generate energy. So there are many uses for that particular purpose, but for food applications where we need to be able to sanitize these membranes, you know, cellulosic membranes we know are not the best ones because they don't have the highest chemical resistance. So we see more activity now in development of membranes for food applications. So my expectation is that as that happens, we will see increased interest. And this is, something that's truly brand new. You need to make sure that it works for your product. Not everything will be concentrated by this process. If you don't have something that's thermally sensitive, you still can use thermal evaporation with partial vacuum. If you don't need to reach too high a concentration, you can use reverse osmosis. There is also freeze concentration that some people use. So there are choices, and this could be worthwhile for some products that are challenging to process using other methods. So I'm not trying to say that this will be the complete replacement of thermal processes. No, we actually know from experience that there are niches for individual technologies, and I would view this as such.
Thank you. I have a question from the audience. It says, high pressure in reverse osmosis may affect the nature of the proteins in the milk or any other beverage with high concentration of proteins?
That's a very good question. It doesn't really have that effect. You could have actually changes in milk protein structure using high pressures, but more in the at much higher pressures. In high pressure processing, for instance, we do see those changes, but we're talking about much higher levels, orders of magnitude higher. What happens in reverse osmosis of milk, for instance, you can have binding of proteins to the membrane, and that would affect the performance of the membrane itself. But overall, we don't see that unless you use a very high temperature. In that case, it could affect the protein.
Okay, and I had another question about the materials of the membranes that you normally use. Is there, of course, the structure of the membranes will affect, I assume, the efficiency of the whole process. Is there, do you construct the membranes, or is there like a specific, like cellulose, as you said, or is there a way that you can build up and model perhaps and a specific membrane to be used?
Good question. Unfortunately, we don't make our own membranes. We use commercial membranes. My group is, in fact, looking at the moment at maybe manufacturing some membranes, but they would have somewhat larger pore sizes. We've worked with electrochemical processes like anodization to create some structures with defined pore sizes in the nanometer range, but those would be a little too open for forward osmosis, reverse osmosis. I don't necessarily say we will never do that, but it hasn't been our focus. So we rely on commercial membranes, and that's why we are as limited as everybody else in terms of what materials we have. But we also collaborate as researchers with other groups. So I know of people who are interested in developing better osmosis membranes. So if there is anything that's new on that front, I will let you know.
Perfect. Yeah, I was thinking something about, I don't know, 3D printing and a specific pore size, but yeah, I was just.
Well, that's a very good thought. It's just the resolution of the printing has to get to that level, because here we have very, very tiny pores, and that's the problem with these osmosis membranes. And I didn't talk much about this, but if we think about these membranes that are used in membrane separation, we tend to think about them in a simplified manner as, cylindrical pores maybe that go through and through. That's not like that. It's more like an interconnected, structure. It's more like a sponge in the end. And depending on how different membranes are made, some of those openings are in a tighter range than in other manufacturing processes. So that's where the challenge is. We simplify for, let's say, modeling, for simulation, we consider them as cylindrical pores, but they truly are not.
Okay, I see that. I have another question from the audience. It says, what's the shelf life difference between reverse osmosis and forward osmosis membranes?
Is it the question about the product or the membrane?
I assume it's about the membrane.
So it truly depends on the hours of use and the cleaning that you use. Now, our use here is for research. So we really put a lot of pressure on these membranes, but we, figuratively speaking, so we take them through extreme conditions and we do a lot of testing, and what we do here is not directly translatable to industry, where they would use them in maybe an optimal range and they would be more gentle with membranes than we are. On the other hand, we actually don't put so many hours on them either, so not so many hours of continuous use. It's truly comparable in terms of how long we use our membranes. For reverse osmosis, you have the added pressure, literally, of the process that can lead to some compaction of the membrane. You don't have that in forward osmosis, but in forward osmosis you have a little bit of a weaker structure, so it's give and take there. Yeah, but they're comparable because the limitation is in the end is that there are cellulosic membranes.
Okay. Two last questions. What will be the effect of volatile compounds like vitamin C during reverse osmosis or forward osmosis, and will the long processing time affect these compounds? This was one question.
Yeah, so they are, vitamin C is a thermally labile compound. It's not volatile, but they are not changed. This is again a physical process. Vitamin C would be rejected by the membrane, so it would not go into the permeate, it would not go into the draw solution, so it will stay completely with the product. It depends on how you handle. Of course, even light can lead to changes in vitamin C, but we work with closed systems, so it wouldn't be exposed to any of the elements otherwise. But the actual process would not have an effect on vitamin C unless you work at high temperatures. So if you are concentrating at 50 degrees centigrade or so, you may see some changes. But if you work at refrigeration temperatures, as we tend to, the process itself wouldn't cause any changes in vitamin C.
I think that the question was more directed to the processing time, this long processing times that it will take. But if it's in a closed environment, I would say it's not affected.
Yeah.
Okay.
And we want to minimize that processing time anyway.
Sure.
Again, we were limited by the small surface area. We have half a square meter of membrane in the small system. We'll go to much more than that in the large system.
Sure. And finally, is it possible to modify the permeability of the membrane during the process to change the pore size?
Well, we actually hope that doesn't happen during the process, because we really want the same performance at the beginning and at the end. We only want, in these processes, we only want water to go through. So some small monovalent ions might go through, sodium may go through, for instance, but we actually do not want that to happen. And it could happen in, for instance, for osmosis, if you actually compress your membrane, so it's a smaller permeability, but we don't want normally changes to occur.
Sure. Okay, well, with this, we are finishing our webinar. Thank you so much, Dr. Moraru, for your talk. I do have one last question, if you have the time, maybe 1 or 2 minutes. Okay. It says forward osmosis has some restriction in food use, and if some food can be affected by the membrane.
Can you repeat the question, please? I'm not sure.
Yes, it says if the forward osmosis will have some food use restrictions, and if the food itself can be affected by the membrane.
This is a good question. There is going to be a limitation related to the osmotic agent that needs to be food grade. And when we think of forward osmosis, we need to think of the membrane, but also the other element that's new, the draw solution site. And the composition of the draw solution has to be controlled so that you don't have any possible contamination, as I mentioned, from the draw solution into the food itself. So that is, you know, one thing. The other one, the effect of the membrane on the food. Well, sometimes we do see interactions between the actually the polymer that makes the membrane and certain food components. There could be some hydrophobic interactions, for instance, between various you know, food components and the membrane that could accelerate their adsorption onto the membrane. So that might happen. It probably would not affect the overall composition of the product. It may speed up fouling, and it may cause problems with cleaning of the membrane in the end, may make it more difficult to clean. And it could also be that if you, for instance, bind something that is flavor agent, then you don't want to use that same membrane for juice and milk and other things, because you may have transfer of those compounds into the next product if that were to happen. But it shouldn't really impact much the composition of the final product.
Okay, great. Now, yeah, thank you so much for your exciting talk. Thank you for all of the participants. And please keep tuned and check our website and Facebook for some more information regarding next month's presentation. It will be in charge of Dr. Kokinis from Purdue University, and
my former mentor from Rutgers.
Yes. I didn't know that. Great. Yes. So yeah, we'll be having him. I think he'll talk about rheology and viscosity. I don't know yet the topic. I'll make sure that I'll send the information soon. And again,
thank you, Vera, for the organization. And I would like also to thank the audience for your time and interest. And if you have additional questions, just reach out to me directly. Thank you, everyone.
Thanks. Bye.
Bye.